Morning. Good morning. No, not enough energies, yeah? Good morning. All right. How's it going? Do you have any snack? You have any snack? Yeah. Good, good. So we're going to continue where we left off yesterday, yeah? Okay. So after we get the recordings, what do we do with them was what we were discussing yesterday, right? Right? That's where we stopped. So many of you came up with these in when you did your exercise, right? Right. So once you get the data, you pre-process the data, right? And then you do feature extraction, then you do some kind of pattern recognition, right? And then you post-process the output, right? So so we're going to go into some detail for each of these steps, okay? Some of you may know already these information, okay? So the first one is in the steps to prosthetic control. The first one is data collection, right? Acquisition, right? First, you have to get the signals, right? So there are two kinds of electrodes, gel electrodes and dry electrodes, and there are also active electrodes, right? What are active electrodes? What are dry electrodes and gel electrodes? Dry electrodes are just electrodes. You don't put any gel, okay, on the skin. You just put them snap on like that, and you start recording the signals, right? But before you do that, usually you clean the skin with an alcohol swab or something to get rid of the dry skin, which acts like an insulator in between the signal and the electrode, right? You do all that. But for gel electrode, um, you don't have to do that. You can put the gel on and you can start recording the signal. And that gel increases the conductance and it also increases the flow of electrical currents. Okay. And so yesterday we saw in one of the slides, we saw what is the voltage range of a muscle signal? Does anybody remember? What is the voltage range of a muscle signal? Hmm? What is the what's the scale? What's the range? Millivolts? Anything else? If okay, so you're giving a number also, yeah. So yeah, microvolts to millivolts is the signal that we're recording, right? Okay, so and then active electrodes. Active electrodes are where there are filters at the site. Okay, so they don't have to travel all the way to a base station. They're active electrodes, meaning they're filtering done at the site. Okay, so these are active electrodes. And then there is, of course, A to D conversion because these are analog signals, right? Yeah, these are analog signals. You have to convert them into digital signals, and then you feed them into a PC, right? Yeah, into a computer. And then the processing begins, okay? And yesterday there was a team that said notch filter. Notch filter. Yes, yes, you said notch filter, remember? Yeah. So we'll talk about that a little bit now. So first we have to do filtering, right? We have to get rid of noise, right? What is ambient noise? Right, right. So any examples for that? What is ambient noise? What is ambience? Ambience is environment, right? Right? External environment, right? Okay. And what is ambient noise? Huh? Lights, power line, power line, lights. What else? Sounds, yeah, yeah. Yeah, what are all the noises present in the environment? That was the question. Yeah. And there's no option E that says all the above. Okay. I want to hear from you. What are they? Okay. Sometimes if you are recording a EEG right here, okay, let's say we're recording EEG right here. What are all the noises you can see? Yeah, not air, but the AC itself, the unit itself, right? So these are all the ambient noise factors that you have to filter out. Okay, all right. And then ma'am said there is power line noise, right? What is that? What frequency is that? Huh? 50 hertz. 50 hertz? Yeah, it's 50 hertz. Okay, okay. So here it is 50 hertz, and in the US it is 60 hertz. That's right. Okay. So to get rid of that, so there's only one frequency where it peaks, right? And in order to get rid of that, you have to use a filter that is like that, right? And what is that called? What is that called? The last row, yeah? Notch filter, right? You said that yesterday. Okay. So so this is good, right? So there is a 60 hertz noise. You use 60 hertz filter, 50 hertz noise. You use 50 hertz filter. You get rid of the noise. Okay. But the unfortunate thing with the way we compute FFT, because they are harmonics, right? So that 50 hertz will keep coming in multiples of 50s. 50, 100, 150. So for us in the US, it is 60, 120, 180. It keeps repeating like that. So we have to use notch filter repeatedly in order to filter out that noise. So that is notch filter, right? And then there is transducer noise. What is that noise? What's that? Converting from a non-electrical to electrical signal, there's some noise. But this is electrical signal. Muscle signal is electrical signal. We are recording action potentials, right? Action potentials are like weaker voltages. Yeah. So these are electrical signals, isn't it? So then what is transducer noise? Trans that isn't that an ambient? Isn't that environment? Right? That's environment noise. That is ambient. It's a good one. That's we forgot about that, right? If you put an electrode and if it is moving, that also will create some noise, right? That's a good one, but that's in the first category. Yeah, but what is this noise? Transducer noise. Yeah, yeah. The probes, yeah. So the device itself, if you're recording, if you will be using an amplifier, right? We saw that yesterday, right? So we'll be using an amplifier and we'll be using some type of a scaled up amplifier because you have to process all these signals. If that device itself, if it is heating up, right? Or if it has a fan, the transducer itself is putting some noise into the signals. We need to be careful of that too. So we need to filter that transducer noise as well, right? And that's where the active electrodes come into picture, is that the motion artifacts, sometimes they filter out those right here. So they don't even reach the A to D conversion and the amplification later. Okay. All right. So, and then comes feature extraction, right? And then you want to extract features. What type of features are these? So yesterday we saw some of the equations for these, right? Minimum absolute value, waveform length, and one of our favorite is root mean squared, right? RMS, right? So root mean squared, and also frequencies, right? So frequencies and also time frequencies, all this can be used as features, right? So, okay, so we know that these are features. So what do we do with these? You have features, but what do we do with these, right? So if you perform, let's say if you perform a movement like this, then we know that these features are varying like this, okay? So there's a pattern in these features. For a certain type of movement, there's a pattern in these features. There's a modulation in these features. So then you start matching, okay? For such a movement, you're creating such a pattern, right? And then for another type of movement, you have another type of pattern. And then that pattern recognition is what you're learning, right? So once you learn that pattern recognition, what are we going to do next? You have to teach it to a machine, right? And that is called machine Machine is learning, not me, right? Not you. Machine is learning, right? Machine is learning. Yeah. So that machine learning is in that big umbrella of what is that big umbrella above machine learning? Correct. Yes. Artificial intelligence. Okay, which is taking away all our jobs. Yeah. Artificial intelligence. If this is a computer science, right? Building. Yeah. Is this so all the coders, they are losing jobs left and right with AI. Okay. If you're simply a coder, AI can do it for you, right? 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 How many of you do any coding courses? Nobody? Nobody's doing any coding courses, programming language courses, right? When you do that, do you use AI? Give me this code. Yeah, yes, yeah. Okay, good. At least we are admitting that, right? If AI can do it, why do you need a coder to do it, right? So now there is agentic AI. So you can even put people, people, virtual agents to do your tasks. Huh? So so AI has taken that. And so there's a humanoid robot that taught a course in spring 2024. Spring 2024. So January 2024, there was a humanoid robot that taught a course in Harvard. Mhm. Okay. So already my job also, huh? Coder job, AI. My job, AI. Now what's left? Mechanical engineers. I thought mechanical engineering might be tough, but huh? Mechanical engineers are also not safe. So we saw last year, we saw Hyundai, the car company Hyundai, right? And all their cleaners, automation engineers, they're all humanoid robots. They can change oil, they can fix the car, they can change the tires. All those are humanoid robots coming, working, and they can do all that. Okay? AI robots is embodied AI, right? What is AI? AI is a piece of software, but how does it act? How does it interact with the environment? By robot, right? So embodied AI is robots. Yeah. AI and embodied AI. Embodied AI is robots. So so that job is also gone. So what is left? Huh? So you know what is telesurgery? So you gave that example, remember? um, Controlling robots far away from you, telesurgery, even Da Vinci robot from Johns Hopkins. We saw that, what, 10, 15 years back. And they even used it on a patient who was in Afghan war. Okay, so even that is taken over by AI. Robots taken over by. So then what is left? What will we do? Huh? Develop robot. So that's a good thing to do. Yeah. So so that's a very good answer, sir. Thank you. So whenever we did IT in the back, right? So computer science we used to do in the back. Now we will do AI. Huh? Now we'll do AI. Now we'll do robotics. Yeah. So we'll ride that wave for some time. Okay. And we'll bother about what we're going to do after that later. Okay. All right. But here is one thing that I think I told you in the first part of my talk, right? Something interdisciplinary is very hard for AI to replace. Okay, something interdisciplinary, it is very hard for the AI to replace. So be as multidisciplinary as you can. Of course, core strengths, core skills, yes, but be as multidisciplinary as you can. Okay. All right. So now, once you do that pattern recognition, machine learning, AI, once you do that, right? Once you do that, then you do post-processing, and sometimes it could be real-time processing, right? If it is offline prediction, it is for offline analysis, right? And it is for online control, it will be real-time processing, right? Is there a difference between offline and online? Okay, the sleeping batch. Can you answer my question? Is there okay, I'm sorry, I didn't mean to put you guys on spot. Is there a difference between offline analysis and online control? Is there a difference? Yes or no? First. Huh? Yes, there is a difference. What is the difference? Online? Online means online, offline means no online. We should give a gold coin to her, right? Not even silver. But thank you. Thank you for answering. Yeah, yeah. Hmm. Uh, uh, yeah. Same thing what she said, you said it in a different way. Just, huh? Platform depends. So that's detail, ma'am. That's devil detail. I'm not asking about that, right? Okay. Huh? No, I'm just teasing you. You did give more detail. Yes, you did. Okay. So but what is the difference? So when you're doing offline analysis, you have a lot of time, right? You get all that data. You can take multi gigabytes of data, take a lot of data, process, right? And come up with answers, right? So you have your time at hand, you have a lot of data at hand, and you can arrive at. So is that important? Is that important? Yeah, it is important, right? It is important. But when you want to control something in real time, you don't have that much amount of data, right? You don't have that much amount of data. You have to process real time, whatever samples you're getting, 500 samples, 1,000 samples, right? You have to process that in real time to control something in real time, right? So major difference between offline and online is huge data sets, huge data. And then when it comes to real time, you don't have a lot of data. So then how do we handle this? If you don't have a lot of data, that means you're ill-informed, right? So you don't know anything about the data. Then how do you control something? What do you do then? Yes. Yeah. Yeah. Very good. You answered that. Yes. That first like an arrow. Okay. Very good. So take all that offline analysis, take all that data and train a model. And that model, right? If it is lightweight, that model you can use in real time. Okay. So that's why offline analysis is important, right? And then, but with that offline analysis, let's say you publish a paper, you do something, that's not enough. That should translate to real time, right? Is that okay? Yeah. Or did I say the same thing she said in a different way? Huh? Okay. All right. So here I'm going to quickly show you. This is a very old video, but I'm going to show you this online finger control using surface EMG signals. Bless you 3 times. So we're recording EMG signals from forearm. And say, are you able to see what's happening in the video? In the computer monitor, you see something moving? Yeah? So what is the task? So watch the video. I'm going to ask you. Watch the video. I'm gonna ask you. Okay, so what was the task? Green dot? Right. So green dot is pointing to one finger, and you have to flex that finger. That is the task. And you have to do it with muscle signals, right? Instead of moving your fingers, you have to use muscle signals and control that virtual robotic hand. That virtual robotic hand is free. This is called VMPL, okay? Virtual Modular Prosthetic Limb, okay? So if you want, you can get it for free. VMPL, okay? So you can use it. Pune batch, you were asking for some projects. You could use this in one of your projects, right? VMPL. And the good thing with this is exactly same interface as a physical arm, okay? So you need to control the physics of it to control this virtual limb. Okay. All right. So I'm going to play that video again. And this time, try observing not just the task, but the performance. Okay. So how is it being controlled? What is the quality? Is it good? Is it bad? What is it? Okay. And also pay attention to the finger movements. Okay. All right. How was the control? Was it good? Was it bad? How was it? What did you see? Did you like it? Was the control good? No.
When it's pointing out a lower finger and ring finger also going along with this thing, sir.
Right. Did we talk about that? Did we talk about that? What is it called?
Some move separately and another one
Wait.
along.
Wait. What is that called? When he said when you're trying to move one finger, the other finger is also moved. You see, try moving your ring finger, all of you. Huh? There was a term for it, right? You guys remember? We talked about it. What is it called? Huh? Huh? There are like 4 or 5 people. I cannot hear anything. Huh? You remember? There was one word. The answer is one word. No, not dimension. Constraint. Okay, biomechanical constraints, but there was a word for it. Degrees of freedom. Synergy. Okay. Enslaving. Remember? Remember that? Enslaving, right? So you move one finger, other fingers are also trying to come along. We didn't ask them to come. They're coming along, right? So this is called enslaving. And they actually put in some biomechanical constraints into that limb. So that it can actually it can actually act like a natural limb. Okay. So it's not a problem, but it actually is mimicking human hand. Okay. So it's not a problem there. Okay. Okay. And then when the hand was trying to be still, there was those movements, right? You saw those movements, yeah? So that's not good, right? That's because EMG is very noisy, and those noise is somehow entering into the control of the joints, and that's why you see those variability in the joints, okay? Those are not desirable, and you could clean up with filters, and you could clean up with better signals. If there are better signals, you could clean up, okay? So, all right, okay, so and then the next question, okay? And this is the last slide for prosthetics. We'll switch to neuroprosthetics, okay? Which is even more exciting, okay? So, who needs prosthetics? Who needs artificial limbs? Amputees. You said individuals with amputation, right? Okay, individuals with amputation, okay? Who doesn't need prosthetics? Huh? Thank you. So the physical therapist, straight $1 million answer. Thanks so much. So those who have paralysis, they don't want an alien arm sitting on their shoulder. They have their own arm, right? Somehow or other, they want to use that, but they don't want to use a prosthetic. Okay. But if they're in wheelchair, it is different. So then you can mount a robotic arm to a wheelchair, and that can help them with their tasks. But that's a different case. Okay. So if you want to use your own arm, okay, if it is paralyzed, and if you want to use your own arm, how would you do that? If you want to use your own arm and it is paralyzed, and if you want to use your own arm, how would you do that? Huh? Okay, thank you. Okay. Please don't give all the answers. I want others to answer too, okay? All right. You didn't hear what she said, right? Did you? Okay. All right, good. So if you want to move, you can go sit next to them and you can move it, right? But you don't want to do that all day. And how do you move it? He himself, with the other hand, he can move. So that is it. This is to God, right? The innovation. So how else? How else can we move? Will that person be happy if he's doing that? Let's say you help move all the time. Will that person be happy? No. If he's using the other limb, will that person be happy? No. Then how can we make it happen? How can we move that limb? No ideas, really. We're all engineers here. How do you make that paralyzed limb move? So what is moving this? What is moving this? How are we moving this? Healthy controls. Healthy control. How are we moving this?
We are giving it signal to move that head to from the brain to the head.
Yeah.
So it's moving like this.
Okay, good. Yeah. Very good, very good. So in the case of individuals with motor disabilities, so what you said plus what she said is that there's muscle activity, right? There's action potentials that are firing. And flexion for us to pull, right? Right? And that muscle activity is reduced in individuals with paralysis, right? So that electrical activity is reduced. The electrical activity is missing. What can we do? We can inject electrical activity and help that muscle to add more power to it, right? And that is called functional electric stimulation. It's called FES. Okay, please write that down. FES. It's called functional electric stimulation. Okay. So that is good. That is good, but what are muscles pulling? What are muscles pulling? No. What are muscles pulling? What are they pulling? Skeletons, right? They're pulling on the bones. They're pulling on skeletons, right? So this skeleton, right? So that's what Ron mentioned. Orthosis. Write that down. Orthosis, right? So this is like an exoskeleton, right? This is an inside skeleton. There's an outside skeleton. It's not an exoskeleton. Put it on top, right? And you can move that, right? So there are two ways you can do this. One is stimulating the muscles. That works for sometimes, but sometimes stimulation does not work. Okay? But then there's no response. And sometimes you use it over time, like that even it's not even not responsive, right? So in that cases, you cannot do stimulation all the time also. Skin burn, and there are all several side effects to this, right? And there's also muscle fatigue, right? Right? So then the other way to do it is exoskeleton. You wear something like you saw in the first part, and exoskeleton, right? Like that. Maybe you wear it like a sleeve. It's like an exo outside skeleton, right? That with motors. Current. Right? Makes sense? Yeah. So there's two ways to move paralyzed limbs. One is functional electric stimulation. The other one is using exoskeletons, right? So here we're going to talk about very, very quickly, we're going to talk about this functional electric stimulation, right? Ultimately, research is moving towards how we can reanimate paralyzed limbs, okay? And we saw in the first part, there was that statistics that physiotherapists shared, right? What number of cases are more, spinal cord injury or stroke? Yeah, amazing. Okay, let's clap. Wow, that's a fantastic. See, you guys have taught statistics to them. Wow, very good. Okay. There are more stroke candidates than spinal cord injury candidates, right? Right? So stroke has a lot of market actually. Okay. And there's a need. There's a need. Okay. So um and that's why I have it on the board that there are greater number of individuals, right? There are greater number of individuals with paralysis than amputation. Okay. All right. So then in those cases, you will see a limb, but that is paralyzed, right? Then now you have to reanimate that paralyzed limb. You can do that in two ways. One is functional electric stimulation, right? So you inject currents into muscles, you pull, you activate them, right? Or the other way is to use exoskeletons, skeletons that are sitting outside, and you can help them. Okay. So very quickly, so we talked about what are evolving prosthetics, and then we talked about different type of amputations. You remember those amputations, right? Upper limb, lower limb, and in those we saw different types of categories, right? And then we saw some prosthetics, and we saw different ways to control prosthetics, and we talked about one specific way, which was the popular way, remember? And that was muscle signals, that is EMG, right? And then we very briefly talked about FES. So the next class is going to be neuroprosthetics. Okay, excited? Yes, let's go for that. Yeah. Okay, what's the time? 12:30. Okay, so let's get started, and we'll go about half an hour, right? And then we'll take a lunch break. Yeah, so half an hour or 15 minutes. We'll see. Okay. Where's that picture from? Any guesses? Who said that? Who said? Who said that? What did you say? Thailand, that's right. Where in Thailand? Okay, but why did you say Thailand? Yeah. This is from Bangkok. This temple is from Bangkok. Okay. All right. Neuroprosthetics. Okay. So then we talked about prosthetics, right? We talked about prosthetics. And what is neuroprosthetics? Pro- Prosthetics controlled by not EEG, prosthetics controlled by brain signals, right? Brain signals could be different kinds. Prosthetics controlled by brain signals. Very good. Okay. So how many of you have heard this word brain computer interface? Yes? Okay. Anybody wants to define what it is? What does it mean? What does brain computer interface mean? BCI is not the right way to use it, but it has become popular. Okay, so some things become popular, some movies become popular. We don't even know why. अरे इसमें कुछ था ही नहीं, right? But it became popular, right? So BCI is a misnomer, and it has been revised to called BMI. Okay, brain machine, right? So brain signals are connecting to a wheelchair, to a robot. It could be computer, right? But it's a machine, right? It's not always computer, right? So, or DBI. What is DBI? Huh? Device, innovation. You're innovating. Okay. Any other guesses? What is DBI? Digital. Let's see. Very good. Digital device. I love this. These are the things that I really like this. See, when you don't learn something from a textbook, then you start innovating. But when you are that's it. You will start thinking in that box, isn't it? Okay. What is DBI? Who said that? Mahindra. Oh, sir. Thank you. Thank you, sir. Thank you. Yeah. So that is direct brain interface. Okay. Direct brain interface. So, but anyway, because BCI is popular, we'll stick to that too. Okay. So brain talks to a computer. Okay, what does that mean, right? Brain talks to a computer. A computer can learn what the brain is doing or going to do. Okay, all right. So a computer can accept the commands from the brain and do some action. Okay, so that is brain computer interface or brain machine interface. So the goal is to provide for people with damaged sensory or motor impairments, we're trying to provide alternate pathways to provide some type of control. So what are we trying to do here? With a BMI, we're trying to bypass the normal pathways, right? We want to try to bypass the normal pathways through peripheral neurons and muscles. That's how we interact, right? With the environment. We're trying to bypass all that, take the brain signals and directly put it to a machine. Okay. So that's what we're trying to do using a brain machine interface. Okay. So um, how many of you taken any neuroscience courses here? Yes, ma'am. Okay. What is your background? What do you do? You are a biomedical engineer. Okay. So you've taken some neuroscience. I thought you guys are all biomedical students here, no? But you have never taken any neuroscience courses. Really? Half Bharatanatyam, half biomedical engineering. So how come? Isn't it important? You forgot the most important part of it, the brain. Huh? Okay. Okay. All right. So not all, I am from computer science and electrical engineering, so definitely they have not taken neuroscience courses. That's why I put in some slides to very quickly ramp up. Okay. So I'm going to teach you only really, really important things that you need to understand the rest of the lecture. Okay. And also to do some projects. Okay. So let's start. And these are different lobes and functions in the brain. Okay. All right. Try to take quick notes. Okay, that's it. Your neuroscience education is done. That's it. Okay. So, question. Okay. Raise your hand if you know the answer. Don't answer it. Okay. Question. How many lobes? Where did they go? Where did the lobes disappear? I told you not to answer, right? Huh? Okay. Very good. Okay. How many lobes? Ah, okay. This time you got it. Okay. All right. So, do you guys still remember the names of the lobes? Yeah? Okay. So, one anybody. Okay.
Occipital lobe.
Occipital.
Occipital. Temporal lobe.
Right? 4 lobes. So one time I was teaching this course in my class, and I played that video, and I asked my students. One of them said there are 5 lobes, and said maybe your brain has 5 lobes, but usually normally we have 4 lobes. Okay, so now I'm going to ask more questions. So there's more detail there, right? There's more detail. So where is the emotion and thinking happening? Nobody raised their hand again. फिर से गए वापस. Okay. Frontal lobe. Okay, let's answer like that. Okay, I don't want to waste time. Okay, all right. So frontal lobe for emotion and thinking. Okay, what was temporal lobe for? Very good, very good. Yes. What was parietal lobe for? Huh? Okay. And what was the occipital lobe for? Vision and vision and vision and visual memory. Yes. Everybody remembers memory, visual memory. Okay. Very good. Okay. Excellent. Okay. So you got it, right? So with that information, and we're going to build. Okay. I'm going to give just a little bit more. Okay. And so what you saw in that video was that this brain is a 3D object, right? Right? We're not in a Zoom call. We're not 2D people, right? 3D, three-dimensional. Yeah. So three-dimensional brain. Yeah. See. So if you were to cut, yeah, so you think of it like a watermelon, okay? Yeah, if you were to cut, okay? I mean, people might not drink watermelon juice after this. Okay. If you were to cut at that central sulcus, okay? If you were to cut at that central sulcus, okay? Then you open it. Yeah? You cut and you open it, it looks like this. Okay? It looks like this, and there are 2 of them. Okay? There are 2 of them. I think it will come later. But right now, let's just look at that, and that is called motor homunculus. Okay? Motor homunculus. And what this represents is where hand is represented, where face is represented, where tongue is represented, different representations in the brain. Okay? All right. So when you look at that picture, what do you see predominantly? What do you see when you look at that picture? What is taking a lot of space? Huh? Both the limbs. Both the limbs are taking a lot of space, right? And the hand is taking a lot of space. What else? Face, right? So facial EMG is what Dr. Karthik does, right? So facial EMG, look at that. Such rich representation, right? Right? That's why we are good at expressing emotions, and we're also good at hiding emotions. Yeah? And then there is tongue, right? Right? Did I share that with you? Hopkins project, they were using tongue as a joystick, okay? Not only as a motor joystick, as a sensory joystick. Yeah? Okay. All right. Now, this might take some time, but please write these steps down, okay? All right. So because this is really, really important, okay? I'm just giving you one example of if, let's say, you wanted to sign, okay? Sign on a paper. What is the thought process that goes in your brain, okay? And what is the activity that goes on in your brain? This is just one example, okay? 1, 2, 3, 4, 5, 6 steps, okay? Write that down, take a picture or whatever works for you, okay? Bless you. Okay. Ready? Yeah? Okay. Even if you take a picture, do write it down, at least later, okay? So you will remember. When you write something, you remember, right? At least for a longer time. And then you'll forget that too, right? Okay. So the first thing is motivation, right? I want to sign my name. I want to sign, right? I want to sign so I can get a check or whatnot, right? So that is the motivation, right? That is the first step. That's the motivation, right? If I sign this, I'll get a check. If I sign this, I'll get money, something, right? Motivation, okay? So that motivation comes from two areas in the brain, okay? One is frontal lobe, okay? And frontal lobe is prefrontal cortex, okay? So that's where the motivation comes from, okay? And there's also this other area, and I think we talked about it very loosely, but there's a deep area within the brain, okay? You cannot see that in this picture because three-dimensional and it is inside, huh? So that's why you're unable to see it. But this is called basal ganglia, okay? So do you remember we talked about this? When does this get activated? I give you an example. When does basal ganglia get activated a lot? Not emotion. Emotion frontal. When does basal ganglia get activated? Basal ganglia is responsible for, huh? This is very funny. We talked about this, huh? Sequence synergy. No, no. No, they are used in motor, but in cognition, where are they used? Uh-huh. Creative thinking is frontal. Frontal prefrontal is creative thinking. Balance. What is okay, you tell me what is balance. Balance. Huh? What was that? What was that region for balancing the movements? Huh? Cerebellum. Maybe in your body it is doing differently. Huh? Huh? Healing. Okay. Yeah, I might need something like that. Yeah. And he might need something like that too. We both have been standing. Huh? Actually, I even forgot to clap today. Let's clap for this. What's your name? What's your name? Huh? Rajashekharan. Amazing, amazing. Thank you. Thank you so much. Okay. All right. So when somebody's gambling, remember we talked about this example. Basal ganglia is a reward and penalty region within the brain. Okay. When you're gambling, this gets hyperactivated, this region, basal ganglia. Okay. All right. So that's where the motivation comes from, is that you want to sign your name. Okay. So that's where the motivation comes from. And the second is posterior parietal cortex. Okay. So we'll call this in short PPC. Okay. Posterior parietal cortex. Okay. And that is here, right? Posterior parietal cortex, right? Yeah. Did I point that correct? Right? Posterior parietal cortex, right? Receives the information from, right next to it is the visual cortex, right? And somatosensory cortex is on the other side, right? And it tries to localize the position of the pen with respect to your body, okay? So if you want to know information about the position of the pen, where do you go? To PPC, posterior parietal cortex, PPC, posterior parietal cortex, okay? And then we have premotor cortex, okay? So where is premotor cortex in the picture? Huh? Area 6, right? Premotor areas, right? Premotor cortex localizes the position of the pen with respect to our hand and specifies a plan of action. So premotor areas are planning areas, okay? So which pen, how fast, etc. These are the details of the motor planning, right? So posterior parietal cortex, PPC, is the place you go to look for position of the pen, right? And then premotor areas, similarly, are involved in motor planning. Yes, okay. And then comes cerebellum, right? Cerebellum we talk. So what is cerebellum used for? Okay, thank you. Okay. So cerebellum formulates the movement in terms of dynamics. So yesterday we talked about cerebellum balance, also brainstem balance. Okay. But cerebellum is also, you said balance, but I also added something else, right? What is that? Cerebellum is the seat of dash. Fill up the blanks. Cerebellum is the seat of control. Okay. Motor control. Okay. Cerebellum is the seat of the sleeping batch. Amazing. Whoa, you guys. That is the right answer. Okay. If I had gold coins, I will give all of you each one. Okay. That is such an important answer. Cerebellum is the seat of internal models. Internal models. You remember? Right? So, of course, you remember, right? So, what are internal models? So, the outside world is represented in your brain in the form of internal model. So before you do any action like that, okay, let's say I'm moving my hand like that, right? Cerebellum will do it first. Cerebellum will do it first inside and tell you that, okay, if you do it with this speed, if you do it with this force, you will not hit the mic. That is all done by cerebellum. This is the seat of internal models. Okay, that's very, very important. Okay, and then comes the most important. Okay, Mr. Prime Minister. Okay, and that is M1, primary motor cortex. Okay, M1 in the picture. You see M1 in the picture? Yeah, M1 in the picture. Okay, that is primary motor cortex. Okay, M1, primary motor cortex. Okay, that is the one that sends down muscle activation information to the spinal cord, and then spinal cord talks to the muscles. Okay, all right. So M1, spinal cord, and then to the muscles. Okay, so if you want to know muscle information, okay, if you want to know muscle information, where is it all coded? M1, primary motor cortex, M1, in short, M1, okay? If you want to know the position where it is coded, posterior parietal cortex, which is in short, PPC, just remember that, PPC for now, okay? PPC for position, muscle is M1, M1, for that is like prime minister. M1 is like prime minister, okay? So, and then brainstem centers ensure that they maintain the posture and balance so you can reach for the pen, okay? Cerebellum is also in balance, okay? All right, so everybody understood this? Is this good, right? You learned at least one semester neuroscience right here, okay? Okay, this is very, very important. This is very, very important for you to see, okay? Okay, with this knowledge, I'm going to ask a question, okay? And then you're going to take a few minutes. Let's see, 12:55. We only 5 minutes, okay? All right, or even less, okay? I need answers before 5 minutes, okay? This is the question. Where would you put an electrode array in the brain, okay? If you want to control a prosthetic limb, or if you want to control a paralyzed limb. Wait, what? No, so the question is, that is the question. They're not, they're, A and B are not answers. There are two questions, okay? Where would you put an electrode array in the brain? So this is the sleeping match again that disrupted the whole thing. Where would you put an electrode array in the brain to control, first question, prosthetic limb? Second question, where would you put an electrode array in the brain to control a paralyzed limb? Two questions, two answers. Okay? Yes, everybody got that? Yeah? Two questions, two answers. Or maybe it is one answer, but prosthetic limb or paralyzed limb is not the answer. Okay, good. All right. Now all those who are laughing out loud, I need you to answer. PPC for paralyzed limb. Okay, so I'm going to write that down. Okay. PPC for paralyzed limb is what sir is saying. Paralyzed limb. And then what was the other paralyzed then? Prosthetic. Okay. Again, this is not the answer. PPC for prosthetic. M1 for paralyzed. So okay, there's like a division. Okay, left side and right side. Okay. Okay. So we're trying to control paralyzed limb and we're trying to control prosthetic limb. They need different types of information. Based on that type of information, we're going to go to that place, right? There are different places. Okay, all right. What kind of information do you need to control a prosthetic limb? To control a prosthetic limb using your brain signals. In neuroprosthetics, this is. Muscles guy, all gone, okay? What type of information do you need to control a prosthetic limb? To control a robotic limb, what type of information do you need? Motors, remote robotics. What type of information do you need to control a robotic limb? Okay, let's put that aside. What type of information do you need to control a paralyzed limb? Muscle information. Thank you. Okay, so to control a paralyzed limb, you need muscle information, right? Where's Ebony? Where's Ebony today? She's not here. Okay, she should have looked at my beautiful handwriting. Even I cannot understand. You want to hear a joke? Yes or no? No, only two people want to. I'm not going to share. Do you want to hear a joke? So one time, all the doctors in New York, there's a medical center called Langone Medical Center. All the doctors in New York, they went out for a protest. Okay? And they were holding signboards and they went out for a protest. Nobody understood what they were protesting about. Why is that? Because they wrote their own signboards. And no one, how will we understand? Yeah? So this is what happens when you become a doctor. So any PhDs here? That's what happens to us, right? When your doctor adds to your name, even though you're not a medical doctor, the handwriting becomes like this. So I was looking at some of your notebooks yesterday. So beautiful, the beautiful handwriting, right? Let's clap for the beautiful handwriting. If you have a beautiful handwriting, that is also a sign of intelligence because it is geometry, right? Yeah. If you don't have beautiful handwriting, that is also a sign of intelligence. Less intelligence, more. Yeah. Okay. Let's go back. Let's go back. For prosthetic, what type of information do you need? Huh? Answer it. For prosthetic. For prosthetic, what type of information do you need? If you want to send a robotic limb to get that water bottle, position information. You need to know the position. For paralyzed muscles, you need to know the information of the muscles, right? But for a robotic limb, you just tell the position, it will go using inverse kinematics, okay? If we have time, we will study inverse kinematics and forward kinematics. But you just need to send that endpoint, right? XY, XYZ, and the arm will go, okay? So for prosthetic, you need position information, right? Okay, now we made it easy, yeah? If paralyzed limb, you need muscle information. If prosthetic limb, you need position information. This is position. Yeah, everybody can read, right? POSITION. Okay. Okay. All right. So now, first question. Question A. It's not an answer. Question A. Where would you put an electrode array in the brain to control a prosthetic limb? So how many are agreeing with ma'am for PPC, posterior parietal cortex? Raise your hand. Okay, only a few hands. For prosthetic limbs. For prosthetic limb. For prosthetic limb, you need position control. Where would you go? PPC. You see, you also agree. Then please raise your hand. Okay. Yeah. So for prosthetic control, you need position control, and that position is encoded in PPC. Also, some parts of premotor areas, right? PPC and premotor areas. If you want to control a paralyzed limb, you need muscle information, right? That muscle information that is sent down to the spinal cord sends down to the muscles, right? So that type of information, where is that coded? M1, right? What is M1? Primary motor cortex, right? PMC or M1 is primary motor cortex. Yeah? Everybody got that? Remember this for the rest of your life. Yeah? This is going to go a long way. Okay? All right. So what's the time? It is lunchtime. Okay. Okay, we're going to stop here and we'll continue after lunch. Posterior parietal cortex.